rigid body motion. So what is a rigid body motion? A rigid body motion. You are doing dynamics in this semester, right? So there is something known as a particle motion, and then there is something known as a rigid body motion. So if you are kind of tracking a particle and trying to see where it goes, still F equals ma is applied to it. So that is dynamics. But instead of a particle, I think in your dynamics class, excuse me, so there is half of the class would be on maybe particle, and then rest of it is based on a rigid body motion. So that means whatever kind of the shape a body starts with, it keeps the same shape. So instead of a particle, there is a block which is moving. So if let's say there is a, do we have an eraser or something? Yeah, a rigid body kind of thing. So if I kind of throw it, it kind of tumbles, goes back and forth, but it does not change the shape. So you can do the dynamics of this thing. So saying that you have some initial orientation, and if you throw it excuse me, with some force and a moment, like say you twist it, give it a moment, and then you also give it a force. So now the kind of tumbling, falling, whatever it will do, you can predict it using dynamics. So there was I think a 1969 kind of movie, Space Odyssey, long time back. So in that there was a block, something like this, rather a slab with some thickness as well. So what it would do is it would go from place to place automatically. There was, I've seen only that clip. So all of a sudden it will appear in space, and that block will be kind of going like this. So the thing was, in that movie they hired a person who knew dynamics, and he calculated how actually this thing is moving. So these days there are softwares, I think Maya is one, and there is another one, 3D Max. All these things, they are already built in. Let's say if you have a ball and you throw it, so it will bounce with some with a certain you can say the actual physics is involved in it. That's what it is. So what I'm trying to say is that these rigid body dynamics, that's another interesting area. And in fluid mechanics point of view, what we have done so far is that a particle is static. Right? Now we'll say that it moves within a tank or something, where that is a rigid body motion. The whole body kind of moves with it. Either it is a rotational case, or it is a container which you have placed in a car and you are moving. So there are two cases. Either things are rotating, and let's say you have a glass of water in the car and you are moving. So the pressure being exerted within that leak fluid in a glass, that is something which is covered here. So what we are interested in is the pressure variation in a fluid with a rigid body motion. In fact, there is an interesting project which I have in my mind. I have talked to few senior guys, senior degrees, that if they are interested. So the idea is that if you are having let's say tea in a mug and you are driving, so if you place it on something so that it holds the cup while you are driving, you are turning and you are kind of making acceleration, decelerations, the tea should not spill out. So it should kind of keep a track of it, and I think one of the equations which will be used are these equations which I'm going to write. So it's just like balancing let's say a steel rod like this. Although you do not have those equations in your mind, but intuitively you know what to do. If it is falling forward, you kind of move your hand ahead. If it's falling backwards, you just... So it's the kind of control technique which is already built in our minds. You don't have to kind of wait that let my brain solve this equation, and when the solution comes, then I'll make a move. So intuitively, or it's a gift of God that things are already embedded in our minds, right? But excuse me. So if you have to develop a control, that you have a chip and that decides what it should do, obviously it will do in maybe microseconds, but still it has to compute. Compute what? How, in terms of displacement, how must be the displacement in order to let the stick not fall, right? If you guys get any chance of doing going for higher education, all those who will be flag bearers maybe. So the point is that you, while taking an advanced controls course, you should, if an instructor is good, he will give you an assignment to design an inverted pendulum. Like this is, like pendulum is like this, but what if it is like this? You have a steel rod and a weight on top of it. Now, the moment there is any disturbance, you might balance it, but there is any disturbance, it will tend to fall. And now you have to control it. So that is kind of the objective there. But in terms of fluid mechanics, you should also know that how a fluid would behave if the car is, let's say, accelerating or decelerating, right? So obviously it is a control within a very small regime. Let's say a car is accelerating from 20 kilometers, it's going till 60 kilometers per hour, right? So there is some degree of freedom which you want to control. It's not like you crash the car and car goes like this, and you are still struggling to keep the T kind of not fall, right? So that's beyond any point. But the car is this, that who cares, right? But this is something at a very small changes, you should be able to control it. It's a very interesting project. I'm not sure if somebody is really going to go deep into it. The people I've talked to, they have some issues regarding these equations. It's difficult. It really requires a lot of dynamics plus fluid dynamics. So that's something interesting. Anyways, we have already done this equation. Everybody is clear? Did I take quiz from this, or that was the other section? Okay. So if I take a quiz of this, you would know it? Okay. So this was something which we did for a fluid particle. Now this K is the direction, this is the direction. That's why this gamma appears here in the Z direction. Okay. Now if let's say we are struggling with the linear motion of something, where is that? Yeah, thank you. Linear motion. So just keep in mind that you are driving in a car and that cup is kind of static, but as you move, the level would change. Another way of looking at things is that you have a cup and you just tilt it by yourself. So what happens? If there's a water level and you tilt that mug, what should happen? The level should also kind of tilt by the same degree, or it should stay the same level. So with reference to, let's say, the road, it will always keep the same level. So the example is, let's say, if this is the case, and now if you, bad drawing, if you tilt it, is this point clear? This is so obvious. right? If somebody does not understand, then the solution is outside the glass, it's not inside, right? Some mental issues then. This is something which you can do the experiment very easily. So that's the point. Now we also studied that the pressure in the same plane does not change. I've given tons of examples. If this is a swimming pool and we are kind of sitting in there, if somebody is swimming at some level, he won't feel any pressure change. The pressure change occurs only when he is going either down or others going up. That's the only kind of situation. So we say that this is varying with Z. Is that clear? So now the point is that since this is horizontal lines, so these horizontal lines will have the same pressure. Let's draw a better and a bigger picture. So as given in the book, this is something, and now I'll do it in a different way. Let's say these are straight lines, and what you are doing is you are kind of accelerating in this direction. This is A of X, this is A of Y, and this is the actual acceleration A. So what it will do is, if you accelerate too fast, let's say if you have a mug in the car and you accelerate too much, the water will kind of rise up at the back. Is that point clear to everybody? And the moment you put a sudden brake, the water will rise up front in that mug or a jar. So this is something what is happening, and we say that the pressure along these lines constant. I don't know why did I write this way, but this is it. So pressure kind of remains constant along these lines. It's a very interesting kind of observation. Okay. In global perspective is going to be partial P, partial Y, dy, partial P, partial Z, it's dz. So if I kind of plug in the numbers, rho A of Y dy minus rho, what happened, G plus AZ dz. Clear? So along this line, let's say this line, is there any variation? Is there any variation? So this dP term is 0 along these lines. Constant pressure lines. These are constant pressure lines. So I can. Right. So, but the point what we are, because of the acceleration, this has happened like this. Along this line, because of that acceleration term. That if it is static, it is true. The moment you apply acceleration, that formula does not hold true. So if you are swimming in a tank, that's in a water tank which is placed on a truck, right? If the kind of level is tilted and you are kind of still swimming within the same level, so the water column above you is the same, which is causing the pressure on you. So in this case, let's say if you are swimming here, right? So the water height is the same as this, the water height is the same as this. This is what is causing pressure on you. Clear? So this is along this constant pressure. We say that change in pressure is 0. And now you can, there is no acceleration, absolutely no acceleration, AY goes to 0, and this goes to 0. So you have a standard dP is z, gamma times z kind of thing. So this is the acceleration which is causing all these troubles. No? Still writing? And one thing which you would like to know is that what is the slope of this line? How many of you know there is a term known as sloshing? Okay, let's say there is, sorry? So if you accelerate it fast, obviously this will go and hit it, and then there will be something like this, a splash, like a splash. If you do it very fast, then this will happen. If you have a sudden break, the T will anyways, it will spill because of that sloshing. And this is a very phenomena where this oil industries, once they are transporting oil, especially fuel, this petrol, they are very much concerned. They are very much concerned about this because of the fact that more it moves, there is more energy, it kind of gets a higher T temperature and it evaporates. And what they do is, let's say if this is a truck where they are kind of moving things, right? If this is the tank, so they have like baffles. Baffles are rubber kind of things. Oil can move. I've drawn a 2D drawing, but these baffles, they kind of slow down this sloshing process. So again, and a very interesting phenomena. All those who are interested in doing their final year project in a couple of years, they will find it interesting. Okay, we were talking about the slope of this line. Slope of the line would be, because we have these axes as y and z. So if this is the slope, right, like dy by dx, had it been x and y, this is, but by just changing notation sometimes people get confused. So nothing to worry, but dz over dy is minus a of y g plus a times z. Right? So most of the time the applications which I have talked, what is ay? There is some number. What is az? What does that mean? At what place can you feel it? Moon, Mars, Mercury, Earth? If you are sitting on a, let's say, rocket and going to the moon, right? A simple example is elevators moving up and down. Although it will not produce any kind of sloshing right away, but if you have a pressure sensor in your cup sitting at the bottom, the moment you will start going up, it will say that, oh, now I have more pressure. Where that more pressure is coming from? That acceleration term. That's az is positive, so that part will increase. Let's write the equation, and then dp dz then becomes, that is something interesting. So similarly, if you are coming down, that pressure will be lesser. And in a free fall, what will happen? Let's say you are coming down the elevator and something happens to all the ropes and pipe. Right. So you can, before you die, at least you will experience a free fall plus no pressure in the mug. A fluid particle that will say that, oh, nothing is happening, but you have to come like a free fall, right? Or all those GCs, if they experience this paratrooping, they can hold a mug and chute does not open. So in those few seconds of your life, you can get an A grade in fluid mechanics. which is otherwise I think not possible. Anyway, so free falling we have already experienced. So this is kind of an interesting phenomenon I just wanted to share with you. And the next thing is a rigid body motion. Oh, sorry, rigid body rotation. We did the linear motion last time. So this is let's say there is a fluid inside it, and this kind of thing is kind of rotating. This is so any fluid particle which is in here, this is kind of rotating, like a spinning thing, spinning cylinder with filled water in it. So now you might encounter a little difficult. In mathematics, you have done r, theta, z cylindrical coordinates. Good. So if you have a question on which includes cylindrical coordinates, you can transform from Cartesian to cylindrical coordinates, right? A direct conversion is something like this, right? And then and similarly all those mathematical operators, they also change. What is an operator? This is an operator, okay. Partial y. So in terms of they are transformed in r and theta, so you have partial r and a combination of partial theta as well. So why I'm saying it, because this del p, this del is an operator,